Hi, the intent of this video is to explain the basic features and usage of EZPy. The version used is 0.2.0. Here we will be showing a simple math function to demonstrate the usage. It is important to understand the basic concepts of EZPy before moving on to real device examples in the subsequent videos. Go to www.techsources.com and click on the Download Now button to download the latest EZPy version. There is no installation required for EZPy. Just move the downloaded zip file to an appropriate folder in your PC and unpack it. The device drivers for the equipments used in the test automation need to be placed in the folder DevicePy files. Go inside this folder and you can see a few Python files. In this video, we will use dummymathsimple.py for our demonstration. The folder evalpy files contains Python implementations of evaluation criteria used in the test automation. Go inside this folder and you can see a file called rangecheck.py. This is the only eval file implemented now and is meant to check if the variables are within defined ranges. We will be using rangecheck in this demo. In the subsequent videos, we will go through the details of implementing device files and eval files. The folder license is for keeping the EZPy license and the related files. This folder is empty in the free version of EZPy, and if the user acquires a paid license or a complementary license, the license file needs to be copied to this folder. Now, double-click on EZPy.exe to open the software. Agree to the end user license agreement to continue. As you can see, it comes with a demo project with a few test cases so the users can play around with working examples. Note that the demo project doesn't need any real device connected. Instead, simple math functions are used as examples. For now, let us close this demo project and start with a new project. We will come back to the demo project later in this video. Open a new project and enter the project name. Add a new test case in the test tree window. Let us name it test 1. Users can add many test cases to the test tree. Users can also edit or delete test cases. The devices window is for configuring devices or instruments for the project. Right-click on the devices and select Add Device. The available device files are listed in this pull-down menu. Let us select Dummy Math Simple. For the upper field, the user can type in any name that identifies the device. The lower field is to select a class from the device file. In this case, there is only one class in the device file, and hence it's already selected by default. In case there are more than one device classes in the device file, the user needs to select the right device class from this menu. Click OK. It opens a dialog box asking the user to type in a multiplier. This is called a device configuration. In Dummy Math Simple, there is only one device configuration, and that is multiplier. Let us type in 0.5 and click OK. The device is now created. Same device file can be used for creating multiple devices in a project. Let us say there are two identical devices connected via Ethernet to the EZPy PC. Though identical, the devices can have distinct IP addresses. Here the IP address can be part of the device configuration. So multiple devices can be created in a project from the same device file but with different device configurations. Note that the multiplier example we showed now is rather simplistic and is only meant for illustration purpose. To modify the device configuration, right-click on the device. All the actions in the device are listed in the device tree. A device can have one or more actions. in this case there is only one action called getResult. Basically, getResult is implemented such a way that it adds two input variables and this sum is multiplied by the multiplier we just entered. This resulting value is the output of the action. In this video, we won't get into the details of defining an action. This will be covered in another video. However, in the later parts of this video, we will show how an action is used in a test case. Now, double-click on the test case to open the test case window. There are four main parts in the test case window: the description window, the scheduler window, the plot window, and the evaluation window. Description window is simply a text field for describing the test. Let us put in a short description here. This is a test to check a simple math function. If you close the test case and reopen it, the description is retained. This is the plot window. There are three areas within the plot window: the left axis, the right axis, and the graph area. The left and right axis are for drawing the scale of the variables plotted. The graph area is for actual plotting of the variables against time. Let us get to the scheduler window next. Before proceeding further, let us look at a few fundamental ideas. Events in a test can be broadly classified as two types: periodic and non-periodic. Take a look at this picture. For periodic events, we just need to know the start time, end time, and period to calculate all the event timings. But for non-periodic events, all the individual event timings need to be defined explicitly by the user, like T1, T2, etc. Coming back to the scheduler window, clicking on the periodic checkbox opens a grid for defining periodic events. And clicking on the non-periodic checkbox opens a grid for defining non-periodic events. Let us first look at the non-periodic grid. The top row is for setting the time label in case users want to use that time label elsewhere. However, this feature is yet to be implemented, so this row is disabled in this release. The second row is for defining the time values. From third row onwards, the variables and actions can be defined. Let us take an example. In the pull-down menu in the cells of the first column, there are two choices: var update or action. Select var update since we first need to define a variable. In the next cell, enter a name of our choice for the variable. Let us call it var a. Fill in some time value pairs. At time equal to 0 second, we need var a as 0. At time equal to 2 seconds, var a as 1. At time equal to 4 second, var a as 3. At time equal to 6 second, var a as 5. Let us hold the last value till time equal to 8 seconds. Click on the play button of the test case to see if the plot comes out right. As you can see, the plotting is correct. Now let us add another variable var b and modify the scheduler window as shown. Click on the play button and see the plot. Note that EZPy ignores the empty cells. For example, let us remove var a at time equal to 4 second. Click on the play button. As you see, the previous value of var a is retained, which is 1. Let's put the 3 back. In the next row, select action. Now go to the devices window, click on get result and select copy text. Do Ctrl V to paste this into the next cell. Action calls need an associated action configuration. Let us add an action configuration. Click on this icon to open the actions config window. Right click on get result and select add configuration. Name it as CNF1. Double-click on CNF1 to open the corresponding action config grid. The action config grid has 2 inputs and 1 output. To check if the action is functioning well, fill in some row values as inputs, say 3 and 7. The value of the device configuration multiplier we entered was 0.5. So the expected output of the action is 3 plus 7 into 0.5, which is 5. Right click on the action configuration and select execute action. You can see that the result is 5 as expected. Replace the inputs with var A and var B. And fill in the output as result. So on execution of the action, the result variable will have value equal to half of var A plus var B. Now go back and click on the pull down menu here. The action configuration that we newly added shows up here. If multiple action configurations were added in the actions config window, all of them would show up in this pull down menu. Select CNF1 in the action row. Note that if a cell is empty, the action is not executed for that timestamp. Another interesting note: if you keep the mouse over an action config, a tooltip is opened that shows the details of the action configuration. Run the test. Let's look at the plot. At time equal to 3, var A is 1, var B is 3, and the result is 2, which is correct. At time equal to 7, var A is 5, var B is 7, and result is 6, which is again correct. One thing to note is the execution flow. The execution flow is as shown in the picture. It is from top to bottom, and this continues for all the timestamps. And if a cell is empty, EZPy does nothing there. You can also use a variable name to define another one. For example, this example works fine too. We can also use math functions from Python's math library. For example, math.pow var a, 2 should work. We shall cover more of these in another video. If you noticed, the output variable of the action is placed in the right axis area, and the input variables are placed in the left axis area. This is the default behavior in EZPy. The user will have the freedom to move them around, but that feature is yet to be implemented. In a non-periodic grid, the rows and columns can be added or deleted. Do a right click to select from the menu. The periodic grid is very similar. Users need to define the start time, end time, and period. Here is a quick example. Let us move the action getResult from non-periodic grid to the periodic grid. Remove the action from the non-periodic grid. And add it to the periodic grid. The start time is 0, the end time is 8, and the period is 100 millisecond. So we configure the periodic grid to call the action every 100 millisecond from time equal to 0 seconds to time equal to 8 seconds. In periodic grid, only the rows can be added or deleted. The event checkbox is for future enhancements. Say the user wants some action to be called when the key A is pressed on the keyboard. But this feature is yet to be implemented and hence the checkbox is disabled. Okay, so far so good. We saw how the where updates and actions are used in the grids. Next, let us see how the evaluation works. This is the step to check if the actual test result matches the expected result. Right-click on the eval tree and add an eval case. Select the eval type range check. Range check is for checking if a variable is within the defined limits in a time window. Double-click to open a window with related parameters. The variable result is expected to have a value of 2 from time equal to 2 to time equal to 4. Fill in the var name as result. Leaving a buffer to account for the latencies in the PC, let us specify a start time of 2.2 and end time of 3.8. Since the expected value of result is 2, let us set the range min as 1.99 and range max as 2.01. Click on the play button to run the full sequence. The eval case did pass successfully. Users can also modify the eval parameters offline and just run the evaluation. Let us modify the min value to 2.01 and max value to 2.02 and run the evaluation. Right click on the evaluation case and select run this evaluation case. In this case, the eval fails as expected. Click on the play button to see the whole sequence once again. Let us add another eval case. And click on the play button. So both eval cases are executed. Users can add multiple eval cases in the eval tree and they will be evaluated in sequence. Users can also evaluate all eval cases offline by selecting run all evaluation cases. Here we only use the eval type range check. Users can define additional eval types based on their need. The details of that would be covered in another video. Now let's open the demo project back. As mentioned earlier, the tests defined here do not require any device connected. Clicking on the play all button would execute all the tests one after another. So, a simple way to check if EZPy is functioning correct in your PC is to run the demo project. Thank you for watching this video. Please watch our other videos to learn more about EZPy.